Today, we are diving into a puzzle that has been a thorn in the side of mathematicians for decades. This isn't just any old problem. Solving it is worth $1 million. We're going to look at a brand new framework that takes a completely radical approach to finally cracking this ancient code. So it all kicks off with a question that honestly sounds pretty simple. If I just give you an equation, how many solutions does it have using whole numbers or, fractions? Could be none, could be a handful, or it could be an infinite number of them. Now, for most equations, that's a tough question, but for a very special type of equation, it's the stuff of legends.
And here they are. These are the special equations called elliptic curves. They have this general form, and for centuries, they've just fascinated mathematicians. Finding the rational points on these curves, the solutions, isn't just a fun little math game. It's like opening a door to the deep, fundamental structure of numbers themselves.
To really get what's happening with this new approach, we've got to first understand where the puzzle comes from. And it's a story about looking at the exact same object from two completely different perspectives.
Check this out. It turns out that every single elliptic curve is kind of living a double life. On one hand, you have the world of arithmetic. Here, we can literally just count its solutions. The number of independent solutions gives us something called its algebraic rank. But then, there's this totally different universe, the world of analysis. In this world, the curve produces a unique song, a complex function that acts like its own personal fingerprint. And a key feature of this song is its analytic rank. So, for the longest time, mathematicians were scratching their heads, asking, are these two worlds just there, side by side? Or is there some deep, hidden connection between the number of solutions you can physically count and the properties of this abstract song you can analyze? Well, the answer to that question is one of the most important unsolved problems in all of mathematics. It's about a bridge between these two worlds that's so profound, it's literally worth a fortune. Yeah, I'm not kidding. This isn't just some obscure problem. The Birch and Swinington-Dyer conjecture is one of the 7 Millennium Prize problems. The Clay Mathematics Institute has a cool $1 million waiting for whoever solves it. So what is this grand conjecture all about? The idea is actually breathtakingly simple. It says those two worlds aren't just connected, they are perfect mirror images of each other. The algebraic rank, our solution count, is exactly the same as the analytic rank, that key property of its mathematical song. Okay, in the language of math, this is the heart of it all. That term on the left, the analytic rank, it measures a very specific property of the song, basically how quiet it gets at one particular spot. And the term on the right is our good old algebraic rank, just counting solutions. The conjecture says these two numbers, figured out in totally different ways, from totally different worlds, will always be equal. This little equation is the bridge. Now, proving this has been, to put it mildly, ridiculously hard. But the research we're looking at today suggests a completely new game plan. Instead of trying to compare the two worlds directly, what if we could build a kind of machine to translate the problem from one world into the language of the other? Okay, let's break this down. Here's the core idea of the translation. First, you start with the L function, that's the curve's song. Then, through some seriously clever math, you translate that song into the blueprint for a mathematical machine. It's this object called an operator, and you look at its determinant. Now, once you have this blueprint, you can basically forget about the song for a minute and just start analyzing the mechanics of the machine itself. And that's the whole magic trick, right there. The perspective completely shifts. The problem is no longer about the subtle, tricky behavior of a complex function. It becomes a much more physical question about the properties of this machine we've just built. And what's so powerful about this is that the translation completely reframes the original question. It turns an abstract puzzle into something you can actually measure on your new machine. So remember, before this, the question was this monster from the world of analysis. How do you measure the analytic rank? How do you know exactly how the L function behaves at that one critical point? It's a notoriously difficult thing to calculate. But after the translation, look at the new question. It becomes, how many stuck gears does our machine have? In math terms, that's the dimension of the kernel of our operator. But think about it. It's a concrete mechanical property that this framework says is exactly equal to the analytic rank we were struggling to find. So now we have a totally new way to get our hands on the analytic rank. The final, critical step is to connect this new measurement, the number of stuck gears, back to the actual solutions we wanted to count from the very beginning. But here's the catch.
it's not a perfect one-to-one match, at least not at first. It turns out the number of stuck gears in our machine does a great job counting all the real solutions, but it also picks up some extra noise, some potential phantom solutions. These phantoms are measured by this really mysterious object in math called the Tate-Shafarevich group, or just SHA for short. So the stuck gears equal the real solutions plus these phantoms.
And this is where the framework gets really, really clever. The way the machine is built, the fact that the operator is something called trace class, it acts like a built-in safety check. This special property basically forces that group of phantoms, SHA, to be finite. And if SHA is finite, for our purposes, its contribution is 0. It just disappears from the equation, leaving us with a perfect match. Stuck gears equals real solutions. So you can really think of the whole argument as this beautiful 3-layer strategy. First, the analytic layer. You build the translation machine. Second, the spectral layer. You connect the machine's stuck gears to the properties of the original song. And finally, the arithmetic layer. You connect those gears back to the actual solutions and use the machine's own design to prove those pesky phantoms don't mess things up. And you know what's really important here is to understand how progress in math actually works. The author, James Robert Gibson, is very clear about it. This isn't a final drop-the-mic proof. It's a roadmap. It's a powerful new framework that lays out an incredibly plausible path to a solution, all by translating the problem into a whole new language. Which just leaves us with this one kind of amazing thought. By taking something as abstract as a mathematical song and turning it into a tangible machine, this whole approach gives us a new way to see the invisible connections that tie the universe of math together. The big question now is whether this incredible conceptual machine is finally the key to unlocking a puzzle that's been hiding in plain sight, inside some of the simplest looking equations we've ever known.